Second objective, piecewise defined functions. Function f is defined by f of x equals 1 minus x if x is less than or equal to negative 1, x squared if x is greater than negative 1. Evaluate f of negative 2, f of negative 1, and f of 0, and sketch the graph. So evaluate means get a number, get a value. And so the answer to evaluate f of is just going to be a number. So the first three things that we're supposed to do, right, 1, 2, 3, is just get numbers. The fourth thing will be to sketch a graph. And so we can kind of see what's coming on sketching the graph. There's going to be, it's a function, maybe you're trying to, and you should be trying to imagine the graph of it. There's a piece to the left and there's a piece to the right. Now, there's a typo. This really should be plus. So 1 minus x if x is less than or equal to 1, x squared if x greater than or equal to 1. So in other words, to the left of 1, to the right of 1. Put the two pieces together and you have one function. Just like putting Kobe Rasmus together with Jake Marisnik, one guy from the left, one guy from the right, and you get one total guy. So here's our function and our quest to evaluate those three things. A function is a rule. And for this particular rule, the rule is the following. First, look at the value of the input x. So, in the first case, it's going to be negative 2, right? That's going to be the x. If it happens that x is less than or equal to negative 1, the value of f of x is 1 minus x. And again, that negative 1 there should be positive 1. Positive 1, positive 1, positive 1. On the other hand, if x is greater than 1, then the value of f of x is x squared. Well, for x equals negative 2, that is less than or equal to 1. And we have that because it's less than or equal to 1, okay, negative 2 is less than or equal to 1. We're going to use the top rule, not the bottom rule. It's the top rule, 1 minus x. So we're going to substitute that negative 2 for x in 1 minus x. X is negative 2. That's just like 1 plus 2, which is 3. So the answer to the first problem is 3. Second problem, f of negative 1. Well, that's also less than or equal to 1. I think for this third problem we want x to be 2. Okay, but second problem, no doubt about it, x is negative 1. That's less than or equal to 1. And so this top rule again will be used. The top rule is take the input and subtract it from 1. Well, if you subtract negative 1 from 1, you have 2. So that's your second answer. Now we have to do the third one. X is 2. 2 is greater than 1. So the bottom rule this time will be used. And the bottom rule is the rule that says you need to square the input. So we square, now if we let that be 2, it is true that f of 0, well, as we've defined it, this is not even right. So let's just get rid of this completely. F of 2, again, 2 is greater than 1, so the bottom rule is used. We don't use the top rule now. Bottom rule is the squaring function. We have 2 squared, which are 4. And so when we do the fourth thing, which is sketch the graph, well, apparently the point 2, 4 is going to be on the graph of f. Now, again, we've got something going on the left, like Colby-Rasmus, something going on the right. So if x is less than or equal to 1, f of x is 1 minus x. And so the part of the graph of f that lies to the left of the vertical line, x equals negative 1, I should say x equals 1, must coincide with the line y equals 1 minus x, which has slope negative 1 and y-intercept 1. Y-intercept 1. Y-intercept 1. Slope is negative 1, which is negative 1 over 1. The rise over the run is rise negative 1, run 1. Rise negative 1, run 1. And so it's good to imagine, what if there weren't conditions? We have a top rule, bottom rule, and then we got these ifs. But what if you didn't have the ifs? What does the top rule look like without the if? And what does the bottom rule look like without the if? If x is greater than 1, then f of x equals x squared. So the part of the graph of f that lies to the right of the line x equals 1 must coincide with the graph of y equals x squared, which is a parabola. So, but again, without the if, what does it look like? Whoops, that point's not on the graph. Negative 2, 4 is on the graph. So without the if, you have this. Now one of these two graphs is going to be used on the left, and one of these two graphs is going to be used on the right. We're going to split it right down here along the line x equals 1. And, well, the top graph is going to happen on the left, and the bottom graph is on the left. Right. Bottom half is on the right. Smash them together. So this is the y equals 1 minus x, and this is the y equals x squared. And so we've smashed these two graphs together, and that's a graph of a piecewise defined function. The solid dot indicates that the point 1, 2 is not, well, let's see, the solid dot is down here. Why? Because here's the key thing. Here's the key thing here. Make sure you get this. The little equal sign is on the top rule, the line, not the parabola part, or piece of a parabola. Now, that indicates that the point 1, 0 is included on the graph. The open dot indicates that the point 1, 1 is excluded from the graph. We couldn't keep both of them, right? We couldn't have 1, 0 and 1, 1. Then this thing would fail the vertical line test, and we wouldn't have the graph of a function. Next example is that of the absolute value function. Recall that the absolute value of a number a is the distance from a to 0 on a real number line. Distances are always positive or 0, so we have a rule: absolute value of any number a is greater than or equal to 0 for every number a. In other words, absolute value can't be negative. And so anything emerging from absolute value bars is not negative. Okay, absolute value of 0 is 0. This number is not negative, square root of 2 minus 1, because it is approximately 1.14. I'm sorry, 1.41. My bad. Square root of 2 is approximately 1.41. And if you subtract 1 from that, you have 0.41, which is positive, and so it's appropriate that that would be the absolute value of something. On the other hand, 3 minus pi is negative. So we're taking the absolute value of something negative when we say absolute 3 minus pi, because that is the absolute value approximately of 3 minus 3.14, which is the absolute value of negative 0.14. Absolute value of negative 0.14, which is positive 0.14, which is positive 0.14, which is the same thing as 3.14 minus 3, which is approximately equal to pi minus 3. And so that's why pi minus 3 is the absolute value of 3 minus pi. In general, we have this definition of absolute value. When we said that the absolute value of a number is its distance from 0 on a real number line. That's more the pre-algebra definition. Here's a more rigorous definition. Absolute value of a equals a, if a is greater than or equal to 0. Absolute value of a is negative a if a is less than 0. And you're like, wait a second. You can't have a negative. Absolute value can't be negative. And so what's up with the negative a there? Well, thing is, that negative a is positive. If a is negative, and a is less than 0 in the bottom equation, bottom rule, if a is negative, negative a is positive. Sketch the graph of the absolute value function f of x equals absolute x. Well, it's just the same thing as absolute a, except with a different letter. It's with x. And so the absolute value function f of x, which in a calculator is abs x. Well, I guess in say a TI-83 we would call it abs x. Again, it's good to imagine the two pieces without the conditions, without the ifs. So f of x equals x, well, that is the old linear parent function y equals x, also known as the identity function. Y equals negative x. The bottom rule, without the condition, without the if, has a graph that looks like this. Well, let's see. X greater than or equal to 0, that's the right. X less than 0 is the left. So we're going to put the right part of the top graph onto the big graph. We're going to take the right side of the top and the left side of the bottom. And that's what we get. So that's the familiar V-shaped graph that we have for absolute value. Application. Cost C of W of mailing a large envelope with weight W. This is a piecewise defined function. Right? Depending on what the weight is, you get a different rule. We get all these different rules. Now, usually in a rule, you see the independent variable. But W does not appear in any of these rules. How many are there? Well, you've got different rules for different weights of envelopes. Between 0 and 1 ounce, between 1 and 2 ounces, 2 and 3 ounces, and so forth. I suppose this rule would hold up to 16 ounces, but who knows? And so we're just going to have to graph each piece and put them all together. Now these are constants, and so what do we know about the graphs of constant functions? Well, they're horizontal lines, and so we're going to take pieces of horizontal lines and make a graph. And if you have say weight is 1/2 of an ounce, what's the price, what's the cost of mailing it C of W? Well, it's 83 cents, right? Because 1/2 is between 0 and 1. So 0.83 of a dollar, or 83 cents. And the 0.83 is on the graph. If your envelope weighs 3/4 of an ounce, what do you pay? Well, you pay 83 cents. And so the 0.3/4, 0.83, that's on the graph. And that's why we get these steps. You can go all the way to 1 ounce and you're still paying 83 cents, but if your envelope weighs any more than 1 ounce, strictly greater than, the rule says your cost moves up to $1 whole. And so that's how we get the steps. And there are any number of steps to this graph, the graph of a piecewise defined function, which is just a transformation. It's a transformation of the greatest integer function that you might remember. You can see why functions similar to this one are called step functions. They jump from one value to the next. And so there is an application of the freaky greatest integer function that you remember from Math 13-14. So it's interesting how these things get applied in real life.